Okay. We're gonna discuss the condensed nearest neighbor algorithm. So at a high level, what does it do? It takes your original data set and condenses it to a much smaller data set by throwing out a lot of data. Okay. And now you treat this condensed data as your full data set, and you run your nearest neighbor classifier with respect to that condensed data set. Okay. And hence, condensed nearest neighbor. Okay. In fact, we usually abbreviate this to CNN, and it's definitely a newsworthy algorithm. Now, I just want to mention quickly that the condensed data that's produced by this algorithm depends on your choice of k. So if you run it with k equals 3, let's say, okay, and then if you run it with k equals 5, you will generally produce different condensed data sets. They might even have very different sizes. So you need to know what value of k you are using in order to run the condensed nearest neighbor algorithm. Okay, you can't just run the condensed nearest neighbor algorithm, produce a condensed data set, and then decide, okay, I'm going to use k equals 5 with that condensed data. And then maybe I'll use k equals 11 on another day. No, the condensed data is specific to a particular choice of k. Okay, and it'll be a different condensed data if you change your choice of k. Just pointing it out. So I'm going to illustrate with k equals 3. And this data set, nice two-dimensional data set where we can visualize things. Okay, and in general, you have a data set D, which is, we used to call this Dn. I'm just going to drop the n for the moment. We have a data set D, which is, your data set has x values, x1, x2, inputs, xn, and y values, y1, y2, up to yn. Okay. Now, it's important for me to sort of emphasize and for you guys to sort of appreciate that, the nearest neighbor classifier, even though it doesn't look like it produces a final hypothesis, it seems to produce a way to classify a test point, but it produces a final hypothesis. It's just that final hypothesis is, there's no training involved, and you take a test point and you compare with the closest neighbor or the closest k neighbors. Okay? But at the end of the day, this does produce a final hypothesis G sub D of x. Okay? It's a final hypothesis that can classify any x. Okay? And it depends on the data set in a very direct way, because you have to carry around this data set with you. Okay, and we can use this final hypothesis to classify all the training data points. So you can use any final hypothesis to classify your training data. So you can, you can compute the in-sample classifications, y1 hat, y2 hat, and so on up to yn hat. Okay, where yi hat is equal to g sub d of xi. Okay, so you run your nearest neighbor classifier on your data. Okay, and you get yi hats. And in general, it's not necessarily the case that the classifications of your training data produced by your final hypothesis from the k nearest neighbor, for example, for k equals 3, match the target values. Okay. Now, quick pop quiz. When k equals 1, what's the relationship between the yi hats and the yi's? I'll give you a couple of seconds. 1, 2, 3, 4, 5. Pause the video. Okay, if you paused and you're coming back just for the ride, or you paused and you answered, they are equal when k equals 1. Bingo, you've understood the one nearest neighbor algorithm. Fantastic. Okay, because the one nearest neighbor has in-sample error 0. It's all the training points classified correctly, almost by construction. But when k is bigger than 1, that's not necessarily the case. Now, I forgot to mention maybe, but we typically always choose k to be odd for the obvious reason that we want to take the majority of our k nearest neighbors, and it helps if you have an odd number when you're taking a majority. Okay? Otherwise, you need a tie-breaking mechanism. That's more complicated. All right. Okay. So this is sort of the background. This is what k nearest neighbor is doing. Now what we're going to do is we're going to try to produce a subset of this data set, much smaller subset than the full data. Okay, and for this subset we will produce a subset S. Okay, and for this subset you can compute the k nearest neighbor classifier. So you can compute G sub S of x. Okay, and what we would like is that G sub D of x is of xi is equal to g sub s of xi. Okay. In other words, if you use this subset final hypothesis to classify all the data points, then it will indeed be the case that the subset produces the same yi hats. Okay. That's the goal of a training consistent subset. Okay. So now we're going to start this subset. We're going to create this subset incrementally, and we'll start at the simplest possible subset, empty. So we start with S equals the empty set. Standard notation phi for the empty set. Okay, and now we realize that we're running the 3 nearest neighbor algorithm, and it doesn't make sense to run a 3 nearest neighbor algorithm with fewer than 3 data points. Okay, so the first obvious step is to add at least 3 data points into S. Okay, so which 3 data points to add into S? Just pick 3 randomly. So add 3, well, add K, in general K, which in this case equals 3 data points, into S. Okay, so, you know, in this example, I've got some blue points and some red points. Let's imagine I pick 3 random data points. Okay, so let's say I pick this guy, put it in a black box. I'll pick this guy, and I'll pick this guy. Okay, so 3 black points. Okay, and you know, at any time when you have a what we typically call S the working set. At any time when you have a working set, you can compute this the K nearest neighbor hypothesis that's, you know, produced by that working set, G sub S of X. G sub S of X. Okay, so quick pop quiz. What is G sub S of X for my working set, which consists of these 3 boxed points, where I'm running the 3 nearest neighbor. So G sub S is the 3 nearest neighbor algorithm, 3 nearest neighbor classifier using S. So pause the video. Okay, I'll give you 1, 2, 3 seconds. Okay, now if you're coming back, or you didn't pause the video and you're here just for the ride, okay, you should have said that, you know, with respect to these 3 points, the 3 nearest neighbor classifier is a very simple classifier. What is it? It classifies the whole space as blue. Now let's see why. Because you only have these 3 points in your data set, so take any point and find the 3 nearest neighbors. Well, there are only 3 points in the data set, so the 3 nearest neighbors are these 3 points. What's the majority among these 3 points? Blue. Okay, so any point has these 3 as the 3 nearest neighbors when you are restricted to S. Okay, and those 3 nearest neighbors, the majority is blue, so any point is classified blue. End of story. Bingo. Okay. So every training point here is classified blue, and I'll highlight one of them, this guy. Okay, I'll make it solid blue. Okay, so solid blue point, the blue, is classified blue by S. So I've written it in blue to highlight the fact that this solid blue point is classified in blue. In fact, it's true that every point is classified in blue. So you might wonder, why did I pick this solid blue point? So let me write this in the terminology we have there by S. So G sub S of the solid blue point is equal to +1, or blue. Okay, blue, +1. Okay, because blue is +1. Okay, why I highlighted this guy, and maybe you figured it out by now, is let's see what is G sub D of solid blue point. G sub D of, you know, solid blue point. What is that? Okay. Well, you know, for the whole data set, now what are the 3 nearest neighbors? Remember, that's where K is coming in. So that's why I said that K is important when you're running this algorithm. So what is the 3 nearest neighbor classification of this point when you're classifying with the whole data set? Well, you have to find the 3 nearest neighbors. So what are those 3 nearest neighbors? Well, if you're classifying this point, the nearest neighbor is the point itself. Okay, but then what are the next 2 nearest neighbors? There's this guy and this guy. Okay, so if you look at the 3 nearest neighbors of this solid blue point, the majority is red. So this is +1. Sorry, -1. I'm even using red and I wrote +1. -1. Okay, what do we observe? We observe that the current working set S and the data set D disagree on this training point, on that point that's in the data set. So this point, let's call it X star. Let's call it X star, reveals a training set inconsistency. A training set inconsistency. Okay. And so we conclude that S is not training set consistent. So we come to the next step in the algorithm. So you've now got a working set S that's non-trivial, non-empty. So there are 2 cases. Okay. If S is training set consistent, then you're done. You're done. So the other case is S is not training set consistent. And now this is going to remind you a little bit of the PLA. If S is not training set consistent, then there must be some data point, X star, which reveals the inconsistency. So there must be some So then there exists a data point x star and its corresponding y star, which reveals the inconsistency. Good? It must be there. Okay. And in this case, it's this solid blue point. What is the inconsistency? The inconsistency is that G sub D of x star is not equal to G sub S of x star. That's what it means to be inconsistent. Notice that y star, the true classification, the target classification of x star is not coming into the definition of inconsistency. I'm just emphasizing this multiple times because that's a common confusion that students have. Okay. You think that inconsistent means that G sub S of x star is not equal to y star. No, y star is not in this definition of inconsistency. Inconsistency is comparing G sub D of x star with G sub S of x star. Okay, important. Okay, so what do we do about this? Well, we have to add a point to x star. So, now it's very tempting, and you probably guessed that we're going to add x star into the data set S. Okay, but that's not quite right. Okay, it's not necessarily the case that x star is the right point. It could be the right point, but in this example, for instance, it is not the right point to add. Okay, so I'll just note it here parenthetically. Okay, we're going to add. We need to augment S. We need to add a point to S. Okay, and that point is not necessarily x star. Not necessarily x star. Okay. So I'm just adding that parenthetically. I could have just told you what point to add, but let me first, point out that it's not necessarily x star. Now let me show you why. Okay, so you can think of x star as it's revealed the inconsistency. So G sub D of x star is something plus or minus 1. Okay, in this case minus 1, and G sub X of S star, G sub S of x star is the opposite. So in this case plus 1. Okay. So we need to add a point that's going to get G sub X of S x star closer to what it should be. We want to improve the situation with respect to x star. Okay. Now, in order to improve the situation with respect to x star, we need to look at the nature of the inconsistency. So what's the nature of the inconsistency? S says that x star is plus 1, and D says that x star is minus 1. So the classification of the point, the true classification of the point we add should be negative. Because we're trying to get this point to be classified as negative. It doesn't make sense to add positive points into your set S. You should add negative points into your set S. And you see here, this point is positive. So if we added x star, it's not going to help the classification of x star. It's going to hurt, actually. It's going to make it more likely the propensity to be classified as plus 1 will increase. Okay? So in this example, we need to add a red point in. And in general, we need to add a point into S that has the same classification as GD of x star. By same classification, I mean target classification. So we need to add a point into S with the y value. Now this is the target y value, not y hat. The target y value of GD x star. And which point? Add a point into S. Which point? That's where x star comes in. Add the closest point to x star that's not already in S. The closest such point not in S. Okay, now why closest? Because we're trying to improve the classification on this x star. We're trying to get this guy to be classified as minus 1. And because the nearest neighbor algorithm looks at nearby points, we want to add a close point to this guy, which is classified as minus 1, or more generally as G sub D of x star. And so what better point than the closest? Okay. So in this example, we look around the whole data set for among the minus 1 points and look for the closest one to this guy, which is this. And so this is the guy we add. Add this to S, at least in this iteration. Okay? And so this tells you how to add a point to S in order to improve the situation for the bad guy, the bad point that's revealing my inconsistency. And that's basically the algorithm. Now we just repeat. So rinse and repeat in some sense. Okay, so repeat, repeat, repeat until S is training set consistent. Okay, so you might have some questions. First, how do I know that such a point exists? How do I know that there is a point in the data set that's not in S, which has the classification G sub D of X star? Okay, so I leave this for you to rigorously prove yourself, but here's the basic idea, and it's sort of kind of self-evident. Well, you know, the training set is getting this guy wrong with respect to the full data. So the only way the full data can get this guy as -1 when this is +1 is if there are other data points closer to X star, which are -1, that are not captured in S. So those closer data points to X star that are -1 are not in S. So that proves that such a data point that's not in S, which is classified as G sub D of X star, must exist. Okay. So such a point must exist. So this step is well defined. So now the only other concern is, how do I know that this algorithm will stop? Okay. How do I know that you will ultimately reach a working set S, which is training set consistent? Okay, so now we have to look at the algorithm. What does the algorithm do? At every step, either you're done or you add a point, and we know that you add a point. Okay. Well, so how many times can this step be executed? At most n times, because after you execute this at most n times, you have added n points. You have added the whole data set. Okay. And the whole data set is certainly consistent with itself. Okay. If S is D, then we're done. Okay. So we know that this algorithm runs for at most n steps. Okay. And so and whenever it stops, okay, which is either at n steps when it contains the whole data set, or it stops of its own accord, i.e. it stops when S is training set consistent. So theorem, and it's not really a theorem, you can prove it yourself. Theorem. It's a really baby theorem compared to some of the other theorems we have seen. Okay. First, the algorithm is well defined. In other words, this point always exists. 1. Algorithm is well defined. 2. It can only run for at most n steps. At most n steps. 3. When it stops, the working set S is guaranteed to be training set consistent. So when it terminates, upon termination, S must be training set consistent. Okay, and so that's the condensed nearest neighbor algorithm, CNN. Very newsworthy. Okay, it's relatively simple. The basic idea is iterative. At every step, if you're not training set consistent, add a point that's going to improve the training set consistency with respect to the one, at least with respect to the point that, you know, is revealing the inconsistency. So let me show you, you know, the condensed nearest neighbor algorithm for the digits data. Okay, so I'm showing you the digits data. We've seen this picture several times already. So on the left, we have the one nearest neighbor algorithm, and on the right, we have, you know, the 21 nearest neighbor algorithm, so k bigger than 1. Okay, and as you can see, the one nearest neighbor algorithm, more complex decision surface. The 21 nearest neighbor algorithm, more smooth. Okay, so we've seen all these things before. But what we're illustrating now is I'm gonna show you what happens when we run the CNN algorithm, the condensed nearest neighbor algorithm, for the one nearest neighbor and for the 21 nearest neighbor. And there, boom. Okay, wow. Look at how much data is thrown away. And then look also at you know, how reasonably well preserved the full decision boundary is. It's not perfectly preserved. That would be decision boundary consistent. Much harder to accomplish, to remember the entire decision boundary. But, you know, what we have produced are much smaller data sets. Okay, and we can get factor. Sometimes you can even get a factor of 100 or more shrinkage in the data set size. Okay, and, you know, what we know for sure is that with respect to the retained data, the classifications on all the data are exactly the same as if you ran the same k nearest neighbor algorithm with all the data and classified the training data. Okay. Now you might wonder, you know, there are still some spurious looking data points. Those have to do with, you know, the randomness in the algorithm. Okay, so, you know, we start with a random data set, and then, you know, at every we pick we pick a training set point that reveals the training set inconsistency. Well, which one did we pick? So there's a lot of randomness in this algorithm, okay? And, depending on, the specific realization of that randomness, you can get very different results, but generally you get a big shrinkage in the data no matter, what instance of randomness you encounter, okay? And so that raises the question, is it possible to find, efficiently the smallest subset of the data that's training set consistent? And you don't need to restrict yourself to a subset of the data. Is it possible to find the smallest set of points such that if you classify with respect to those points, you will be training set consistent? When those points are not restricted to be data points, sometimes we call them prototypes. Okay? And it turns out that problem, finding the minimum training set consistent subset of the data, that's NP hard. So in a very formal sense, it is a computationally hard problem. Okay, but who are we to complain? We're getting such good reduction anyway, so be happy in some sense. Okay, now the fact that it's training set consistent, especially if you use a reasonably large value of k and you have a reasonably large amount of data, means that the in-sample error is preserved. Okay, and we know that if you've chosen the right size of k, then the out-of-sample error is close to optimal, and the out-of-sample error is close to the in-sample error. And if you've preserved the in-sample error, then you've gotten a good out-of-sample error as well. Okay, so we can also make arguments. Okay, I gave you the high-level heuristic argument, but we can also make arguments that getting a training set consistent data set, okay, will preserve your performance. You're not sacrificing out-of-sample performance. You're definitely not sacrificing in-sample performance. Okay. All right, so that addresses the memory issue. So now we can, significantly lower the memory footprint of this algorithm, of the k-nearest neighbor algorithm. We don't have to carry around the whole data set. We only need to carry around the condensed data set. What you will also notice is that for the different choices of k, the condensed data sets are quite different. And that has to do with the fact that the algorithm intimately depends on k, because, k is what defines g sub d and g sub s. So, we've now got a condensed data set that's good, that represents the full data set. So you can imagine the 5-year-old doing something like this. Anytime a new horse comes, it probably says, do I need this new horse? Well, maybe I do. Or, you know what? I'll keep this new horse in my memory and throw that other one in the dark light. That's useless. Okay. So condensing the data is a very powerful tool. Also, in addition to, saving us memory, it can highlight the important, the useful, the critical data. Okay. All right, so that's the memory issue. It also helps with computation, because now computing g sub s is much faster than computing g sub d. Okay, but let us now specifically tackle the computation issue, how to find the nearest neighbor quickly. Okay, assuming that you've already done all your condensing and stuff, and now the data set is fixed. Okay, and so now it's just an algorithmic question and a geometric question of how do you store the data, and then how do you quickly find the nearest neighbor. Okay. And we'll focus on the nearest neighbor, but the same discussion applies to k nearest neighbor. Okay. Okay, so finding the nearest neighbor. So the algorithmic efficiency issue.